So, welcome to chapter 26.1, which is all about the sun. You just saw a clip from one of my absolute favorite songs of all time, which is The Sun is a Mass of Incandescent Gas, and it's by They Might Be Giants. We'll definitely watch the whole thing in class. And I love that song even though it's not actually scientifically accurate. It turns out the sun is not a mass of incandescent gas, it's plasma. And that's because the sun's core temperature, the temperature at the center of the sun, is about 15 million degrees Kelvin. And that is so hot that the electrons are ripped out of the atoms of gas that make up the sun, causing them to become charged. And that's the definition of plasma. So the atoms that are losing their electrons are hydrogen and helium for the most part. So 70% of the sun's mass is hydrogen and 28% is helium. The other 2% are heavier elements like lithium and beryllium, which are actually made inside the sun from the hydrogen and helium. And this is through the process of fusion. So the sun's energy, the heat and light that we feel and see on Earth, is produced in the central region of the sun, right in the middle, by the process of fusion, where hydrogen nuclei collide at such high speeds that they basically stick together and make helium. So we know that the number of protons in an atom defines the element it is. So hydrogen has an atomic number of 1, meaning it has 1 proton. If you take 2 of these hydrogen nuclei, just a proton and a neutron, the electrons have been taken away by the very high temperatures. If you take these 2 nuclei and you put them under extreme temperatures and pressures, they'll be moving so fast that when they collide, they'll actually come together to form a completely new nucleus that has 2 protons. And if something has 2 protons, it's helium, because helium has an atomic mass of 2, which means it has 2 protons. So, hydrogen, 2 hydrogen atoms can come together and they will fuse, they will undergo fusion to produce a helium atom. And this can also happen to form the heavier elements. So a lithium atom would be 1 hydrogen and 1 helium coming together to make a nucleus with 3 protons, and so on. When this happens, a lot of energy is released. And that energy is the heat and light that we sense from the sun. That released energy, when those heavier elements are being made, is what causes the sun to glow and basically give us everything we need here on Earth. So you would think that all of this great energy being produced in the middle of the sun would make the sun expand, right? The heat and the light that's being created in the center of the sun has to move its way to the outside of the sun and then leave in order to get to us on Earth. So if all that energy is making its way to the outside, why doesn't the sun just kind of expand and blow up? It's because even though there is that outward force of fusion, it is counteracted by another force, which is the inward force of gravity. So gravity is the attraction of any 2 pieces of matter. It turns out that the outside of the sun, the surface of the sun, is attracted to the center of the sun, just like we are attracted on Earth to the center of the Earth. If the surface of the Earth wasn't in our way, we would be pulled all the way to the center of the Earth. It just so happens that the surface gets in the way, and that's why we seem to be attracted to the surface and not to the center. But the surface of the sun is being pulled inward by the great forces of gravity, and that inward force is what counteracts the outward force of fusion. If gravity were too weak, the sun would expand, or if fusion were too weak, the sun would actually collapse under its own gravity. Luckily, the sun is at a perfect, nice equilibrium. It's been around for about 5 or 6 billion years, and scientists think it's going to last for another 5 or 6 billion years. It's right in the middle of its life cycle, and that's because of these perfectly balanced forces. Now, the sun is actually made of parts. Just like the Earth has different layers, the sun has different layers, and there are 6 different parts. The core, the radiation zone, the convection zone, the photosphere, the chromosphere, and the corona. The core the convection zone, and the radiation zone make up the interior of the sun. So these three circles. The core is the very, very center of the sun. So it's this very center ring right here. And this is where fusion takes place. This is the part of the interior of the sun that has the highest temperatures and the highest pressures. So it's really conducive for fusion of hydrogen into helium and then into heavier elements. Now, the radiation zone is the second layer, so it's this layer right here, and the energy that's produced by fusion in the core moves its way through the radiation zone to get to the surface. And as it moves through the radiation zone, it does that in two different ways. It does it through radiation, and it does it through convection. Now, convection's a little bit easier to understand. In convection, energy is transferred from one place to another through currents. So it turns out that heat rises. If you have a hot gas, it is going to rise up above the cooler gases around it. And that's exactly what happens in the radiation zone. In the radiation zone, the really, really hot plasma that's near the core starts to rise, and as it rises, it starts to cool down, and then it will sink so that other hot plasma can come to the top, and then as it cools, it will sink again. And each time this really hot plasma gets to the top of the radiation zone and starts to cool, it transfers that energy into the next layer, which is the convection zone. Radiation, on the other hand, does not require a medium. That means that any kind of energy can travel through a vacuum if it is transferred by radiation. So the light and the heat from the sun that we feel and see on Earth is transferred by radiation because all of that energy just moves through the vacuum of space. It does not require an interaction of molecules to transfer that energy. And the crazy thing about the radiation zone is the energy can take 100,000 years to go through it because of how compact and how complex those convection currents are. So the sun's light takes about 8 minutes to reach Earth, but that's once it gets to the surface. The light you're seeing from the sun is not only 8 minutes old, because that's how long it took to travel through space, it's up to 1,000 years and 8 minutes old, because that light was originally created in the core and had to work its way to the surface before it could leave to come to us. Finally, there's the convection zone and the interior of the sun, and this is the third layer. And in the convection zone, energy moves outward via convection currents, just like in the radiation zone. And it is the smallest layer out of the three. Now, once we get to the surface of the sun, there are three more layers: the photosphere, the chromosphere, and the corona. So the photosphere is the innermost level of the surface of the sun. So it's this inner ring right here. And it's the visible surface of the sun. When you look at the sun, hopefully you're wearing protective eyewear so you don't hurt your retinas, but when you look at the surface of the sun, you're actually seeing the photosphere. It's opaque, meaning you can't see through it, so we can't see through the photosphere into the core. We can only see the photosphere on the outside of the sun. And it's actually pretty thin compared to the other parts of the sun. It's only about 500 kilometers thick. Now, the next part is the chromosphere. And the chromosphere is this outer ring right here. It's just outside this photosphere, and it's the beginning of the atmosphere of the sun. This is where the temperature of the atmosphere of the sun starts to increase, and it actually gives the sun its yellowy color. The yellow color comes from the heat of that gas. If that gas were hotter, it would tend to be more toward the green, blue, purple end of the spectrum because it's more energy. Remember, we said higher energy light is more toward the violet end of the rainbow. And if the chromosphere were cooler, the sun would be more red. Now, the last part is the corona, and the corona is the outermost layer of the sun. It's this part right here, and it's actually the hottest part of the sun. The temperatures in the corona are crazy. They reach like 15 million degrees Kelvin. And because of that, really crazy things start to happen in the corona as well as in the chromosphere and the photosphere. And those crazy things are things that we as astronomers get really excited about on Earth. And those are sunspots, prominences, and flares. Now, a sunspot is actually just a spot on the sun where the photosphere is slightly cooler than the area around it. So these dark spots here they seem dark, even though they're actually very, very bright. They seem dark compared to the rest of the sun because those spots on the photosphere are actually a little bit cooler, so they're giving off a little bit less energy and a little bit less light. Solar prominences are actually really cool. In a solar prominence, highly charged particles, like super ionized plasma, is actually shot off of the photosphere into the chromosphere, into the corona, and it gets caught on the magnetic field lines of the sun's atmosphere. And it will actually get pulled along that magnetic field line and come right back in to the photosphere where it started. And that's why it has this crazy loop pattern. And these loops are not small. You can see this is the size of the Earth here. You could fit a lot of those inside this one giant prominence on the surface of the sun. Finally, there are solar flares. And solar flares happen when highly charged particles and high energy radiation is actually completely shot off the surface of the sun and into space, and it will just keep going and keep traveling until it meets the nearest thing. Solar flares have been known to cause power outages when they reach Earth's atmosphere and Earth's magnetic field, because there's so much energy traveling from that solar flare through outer space that it can actually mess with our electronics, which is kind of crazy to think about. So this is your homework. You have 3 questions to answer about the sun, and we will talk about this tomorrow and have your questions ready.